Hello, hello, hello. So let's give an example about distribution of valuation. So consumers in the market for a given good, perfectly divisible good. So there's infinitely many consumers. The quantity of consumers or the mass of consumers is normalized to 1, right? So triangle distribution. So consumers have valuations between $7 and $9, okay? Everybody that is willing to pay for the good has maximum willingness to pay or valuation here, as I'm saying, between $7 and $9. The consumer with the highest valuation would pay up to $9 for the product. The consumer with smallest valuation would pay $7 for the good, okay? So the density is this function, v over 2 minus 7 over 2 is this straight line. If I plug v equals 7, this is 0. And if I plug 9 minus 7 is 2 over 2 is 1. The height here is 1. And it's a straight line. This is an affine function. It's a straight line. So I can calculate my cumulative distribution in two different ways. First, I can use geometry here. In a given point v, between 7 and 9, this height here is this, right? V minus 7 over 2, this height. So the area of this triangle here is the cumulative distribution, the area from here to here and below the density. So it's going to be 1/2, because its area of triangle is 1/2 times the base times the height. So 1/2 times the base is v minus 7, so this distance here is the entire distance v minus this distance 7. So v minus 7 is this distance here, the base of the triangle. And the height of the triangle is v minus 7 over 2. V minus 7 over 2. Okay? So I have this, if I multiply, I have this formula for the cumulative distribution, the area of this triangle. Now I can do that because here is a triangle. In general, you cannot have geometry. This could be a curve, so you would have to use integration. But if you do the integral from 7 up to v, from 7 to v of your density, so this expression here is my density, right? And if I do the integration v over 2, the integral is v squared over 4. I integrate from 7 to v, and minus 7/2 of v, integrating from 7 to v. And when I substitute v here is v squared over 4. When I substitute 7 here is going to be 49 over 4, minus this one here. Plug v here, 7v over 2. Plug 7 here, 7 times 7 is 49 over 2. When I do the algebra, cancel things, I get this. But notice, this expression here is exactly the same as this. Okay? It has to be two different ways of doing the same thing. Now, price in terms of quantity, right? So I use the formula that we discussed in the previous video. Right, quantity at some value of p here, of course, p between 7 and 9 is 1 minus the cumulative distribution. So 1 is 4 over 4 minus, and then the cumulative distribution I repeat here. Okay, so I can have an explicit formula for that. So yeah, q, it's going to be a quadratic function of p, okay? A quadratic function of p. And if I take the derivative, I can even find the slope, all right? I can even find the slope. So here, if I have prices below $7, everybody, this is 1 here, everybody, all consumers want to buy by prices below 7. If I have prices above 9, nobody wants to buy, right? So perhaps the demand continues here with 0 demand if for prices above 9, and for prices between 7 and 9 I have this expression here. I have this. That's the quantity of consumers that buy if this is the price. Notice that the derivative is going to be a negative number. So if P is between 7 and 9, this is positive, but I have a minus, so this becomes negative. So this is downward sloping. At the derivative evaluated at 7 is 0. Evaluated at 9, 9 minus 7 is 2. Minus 2 over 2 is minus 1. If I use the inverse function theorem, the derivative of P with respect to Q at 7 is infinite, at the 9 is negative 1. So that means that the tangent here is vertical, and the tangent here is like, if I want to draw a tangent line, it would be negative 45-degree angle. Okay, the slope is minus 1 for the tangent here, the slope here, well, it's the vertical. Okay, and it gets each time more curvy. Okay, so that's, and then from, if you know this formula here, for the quantity you can calculate elasticity and other things. Okay. So that's a numerical example of a particular functional form with the triangle distribution of valuations. Okay, see you guys next time. Bye bye.